Hello, class. I hope you're all doing well and staying healthy. And always keep that smile in your face. Thoughts are electric. Today, we're going to look at lesson 3 of our circuitry unit, and we're going to discuss what is a series and what is a parallel circuit separately. Later on in the next lesson, we're going to combine the two. But first, let's master what is a series and what is a parallel circuits. So the simpler one is a series circuit. So a series circuit is pretty simple because the resistors, they all follow one single loop so that each component, there is only one conducting path. So that is the key word, is in a series circuit, the current flows through each of the load or the component one after the other so that there is a single conducting path for current to follow. So single path for current to follow. Now, remember that a circuit has three parts. You have the source, which is the battery or the outlet. You have the path, which is the wire, and you have the load, which is the appliance or the electronic or whatever it is that you're trying to power up. So the resistors, if you have more than one and they are following for the current, there's only one single conducting path. So let's jump right into an example here. The diagram below shows a circuit in which two resistors R1 and R2 are connected in series. So it's always easier to start with your battery or your power source. So I'm going to start with my battery here, and I'm just putting one here, a negative and a positive. And we have two resistors. So I'm going to go 1, 2. There are many ways to draw a circuit, but the key is remember that the current, which comes from the positive, will have to go through this resistor. I'm going to call this one R1. But for this R1 to actually power up or turn on, that current, the one we're tracing here, needs to get back to the negative terminal of the battery or the power source. But in order for that to do that, you see this arrow, in order for it to get back to where it came from, it needs to go through this component, this resistor, R2. So that tells you that there is no other choice. There's no other path for the current to follow. Then R1 and R2 must be in series. So another example that you could do here is do this. Again, even though they may look like they're in parallel, but again, if you trace the current, here we go, it has to go through this one, but for it to get back to the negative terminal, it's got to go through that one as well. So this could be your R1, this could be your R2. There are many ways to draw your circuit schematic. So one path, that is the key thing to remember, is that there's only a single conducting path. So because the two resistors are connected this way, if the current in one resistor is interrupted, the current in the other one is also interrupted. So again, we discussed yesterday in the previous lesson what we call Kirchhoff's rules in circuit analysis. So it's either all on or all off. You can't just choose some to be on and some to be off because there's only one path to follow. So let's say this is a light bulb. If this light bulb is broken, then that one won't work either because it needs to get back to that battery for that to work. If this wire is broken anywhere in the circuit, none of them will work either because there's only one single conducting path. So let's analyze a series circuit in terms of the three important things that we need to look at. We're going to look at it in terms of current, voltage or potential difference, and resistance. So I'm going to draw another example here as we discuss this. And again, this is going to be a follow-up to Kirchhoff's rules that we looked at yesterday. So I'm going to do an example here. Let's do R1, R2, R3, R4. Let's do four resistance here. Four resistors. R1, R2, R3, and R4. So here is our EMF. Here's our potential difference. And you know that the total voltage is going to be coming out of that. That is the maximum potential difference coming out of that power source. So just so we can discuss the cardinal rules for the series circuit, let's give them some numbers. So let's call this, let's make this 10 ohms. This is 20 ohms. Let's keep going higher. 30, 40. Okay, so if you are looking at tracing that current, so you have the voltage. Again, the voltage is the kick. So this is what kicks the electron. Kick is basically the pump or the pressure. This kicks the electron. So I always think of the potential difference or the voltage as the pump that kicks the electrons, much like your heart pumps the blood out of that heart so that it can get all over your body and feed the cells. Okay, and this is the current. So the current would be, this is the flow, this is what's flowing through the path. And this is the resistance. And as the name implies, this is what's fighting the flow of current. So it resists, as the name says, resists the flow of current because it's using it up. It's the monster fangs that are using up that current. Okay, so if this is one conducting path, again, let's trace the electron flow. So it's coming out of the negative, but the current comes out of the positive. That's what we're looking at. We are concerned with the flow of conventional current, not the electrons. So it's going to flow through R1. Again, this is not going to light up until this actually experiences a potential difference. So it has to go all the way and back, and then that will light up. So it actually has to go through a full cycle, not just the current going through here and this is going to light up. No, it doesn't work that way. It actually has to do a full cycle for each of them to work. And as you can see, there's only one path for the current to follow. So there's a current going this way, has no choice but to flow through all the other components. There's the current going through every single one of them. So of course, because the resistors are working together to fight that voltage that is kicking the current out, is going to add up. So the more resistors you have in series, the harder they will fight to resist that flow. So the RT, so we're looking at this part right here. So the total resistance or the equivalent resistance is just the sum in a series circuit. So again, we're looking at a series circuit here. In a series circuit, we just add them all up. So the resistance here will be 10 plus 20 plus 30 plus 40. This is 100 ohm. So I hope that makes sense. They're all working together. They're all lined up and working together to go against that flow of current. So naturally, you're just going to find the sum of all the individual resistance. So you just add them all up. In terms of current, see the current that's going through here is the exact same current that's going to go through R2 and R3 and R4. So regardless of the amount or the strength of resistance, the current is going to be the same. The individual current, okay, the individual I will be the same as the total current. It's the same line. And the reasoning for this is because it is the exact same path. It's the same line. It's just going through that road. Okay, so what is the same in a series circuit? What is the same as the total? Well, the current is going to be the same because it is the same path. Now let's talk about the voltage. Now remember, the voltage is the pump, the potential difference, because it has a negative and a positive. This creates the push or the pressure or the pump that pushes the electrons out of the terminal, which creates the flow of current. So this voltage is going to get weaker because think of it this way. The push is coming from this battery. This is the pump. So by the time it gets through the first resistor is resisting that pressure. It's pushing back. So the push is going through it, but by the time it gets through this first resistor, it's going to be weaker. And then it goes through another resistor that's going to be even weaker, and it gets weaker as it goes through more resistors, because at the end of the line, this pump, let's say you start with 9 volts. By the time you go through the full cycle, you will end up with 0 volts. That is why you have the maximum potential difference here at the terminal, at the power source. This is where your pressure is the hardest, is the highest, because of that difference. The maximum and the minimum, they meet right at the positive and the negative terminal, which is the power source. So it's going to get weaker. So what does that mean? That means that if you add up the V1 and V2 and V3 and V4 in our example here, that is going to equal that 9 volts. Is going to split up. So the volts, the VT is basically shared amongst the individual resistors because they are going to make that pump lower pressure, or it's going to get weaker as you go through each resistor. So that is why you are going to have to split that in a series circuit. But most importantly, what we need to remember is that what is the same as the total current? It is what is the same as the total, whatever that is it a total current or total voltage? It is the current. So the current is the same, the individual current is the same as the total current because it is going through the exact same road. Nothing changes because it's the exact same line. It's just flowing through it. Whereas the volts is the kick, which will get weaker if you have to fight, or if you have to fight through these resistors. So let's actually calculate the current, the voltage, and the resistance in this example here. So given R1, R2, and R3, and R4 value, we have calculated the RT. Keeping in mind this is a series circuit, which means that the individual current is the same as the total current. That is the case in a series circuit. So I'm going to give you a summary later on that summarizes Kirchhoff's rules so that we can always remember what changes in terms of the voltage and the current when you're analyzing a series and a parallel circuit. So now that we know that this is the same conducting path that you're going to have to go through, Let's calculate the total current. So according to Ohm's law, voltage is current times resistance. So the total current then is going to be the total potential difference, VT, divided by the total resistance of the series circuit. So the maximum potential difference that we have, our EMF, is 9 volts in my example here. And we have a equivalent resistance of 100 ohms. Our total current is, calculating it, 9 divided by 100, oops, and you have 0.09 amperes of total current. Again, once we've analyzed the circuit in terms of Kirchhoff's rules, we can actually ignore Ohm's law at this point. We don't need to calculate the individual current because we know that once we have the total current calculated, the individual current is going to be the same as that total current. So if the total current is 0.09 amperes, I1, I2, I3, and I4 are all going to be 0.09 amps. That is the advantage of knowing Kirchhoff's rules, because we don't always have to rely on Ohm's law. So we have calculated the total current, the individual currents. We know the individual resistance and the total resistance. Let's now calculate the individual voltages. So keeping in mind the total voltage is 9 volts. This is when Ohm's law jumps in, because we know that there is going to be a different voltages because of the different resistance in each of these components. Let's calculate the individual voltages. So V1 equals I1 R1. The current is the same, so 0.09 amps times a resistance of 10 ohms. So this is 0.9, we just move it 1 over 0.9 volts. And that is our V1. Let's take a look at our V2. V2 is I2 R2. And again, 0.09 is our current times the resistance is 20. We have 1.8 volts for our V2. And V3 is 0.09 times 30 is 2.7 volts. And last but not least, our V4 is 0.09 times 40 is 3.6 volts. Now, if you were to add up all the individual potential differences of these components, it should add up to 9 volts. And just looking at it, just a quick scan, they do add up to 9 volts. So our calculation proves to be correct. Let's analyze this one last time in terms of the resistance and the voltages. Remember that the R1 is the lowest resistance of 10 ohms. Our V1 is 0.9 volts, whereas the fourth one is 40 ohms and the V4 is 3.6 volts. So think about that. Why do we need to have more volts where there is a higher resistance? Think of it this way. The resistor is fighting that flow of current, and the potential difference is pushing that current to go through that conducting path. So if you are going to have a stronger resistance, a stronger opponent, it's fighting you back, you're going to need to push harder to fight back. And that is why the one with the 40 ohm has to have the one with the highest voltage or potential difference, because it needs to have a higher push because it is a stronger resistance. But with a series circuit, the current, individual currents, are going to be exactly the same as the total current, regardless of the strength of the resistance, because it is the same path and it's just flowing. It is the push or the pressure or the voltage that is going to be weakened. So the 9 volts that is coming out of this EMF, okay, so I'm going to elaborate on some terms at this point, and I'm just going to make this picture a little bit larger so that we can add some vocabulary here. So we have, just looking at this picture. All right, so we have your R1 going this way, R2, R3, and R4. Okay, so here is our larger version of our circuit. So you got 9 volts of EMF, R1, R2, R3, and R4. Now this is 10 ohms, 20 ohms, 30 ohms, and 40 ohms. All right, so let's just elaborate on the EMF. So you've got this 9 volts and it's pushing that current. So this is the flow of current from the positive terminal. At this point right here, if I were to measure with a device called a voltmeter, so I'm going to have to put my voltmeter right here. You notice that this is actually not in series because it has 2 different paths, one going this way and one going this way. So if I were to measure this, 9 volts is going to enter this resistance here. But what comes out, what is our V1? V1 is 0.9 volts. So it's going to use up 0.9 volts. So what comes out here is 8.1 volts because this R1 is already using up 0.9 volts. So this one is called the voltage drop because you're dropping 9 volts, and what comes up is called the voltage rise. So the voltage rise is 8.1 volts. So as the current continues, it's going to go this way. And again, you still have 8.1 volts going through the R2. And what comes out of it, now remember we calculated the V2, and our V2 is 1.8 volts. So it's using up 1.8 volts. So the V drop right here, you're dropping off 8.1 into this 20 ohm resistor. What comes out is going to be 8.1 minus 1.8 volts. And so you have 6.3 volts left. You see what's happening? The pump or the pressure is getting weaker. Let's move on to R3. Remember here, you still have 6.3 volts of V drop. This is how much you're dropping off. R3 is going to fight that off. That's why I call it monster fangs. You see that? It's fighting off the 6.3 volts. So once it's done out of this R3, it's, what is our V3? V3 is 2.7 volts. So now you have 6.3 minus 2.7 volts, and you have 3.6 volts left. That's your V rise. Okay, moving on, current goes through this way. And again, it's going to encounter R4, and your V drop is, you still have the 3.6 volts V drop, and the V4 is 3.6 volts. Look at that. So once it's done going through this R4, this already has 0 volts. And it has nothing left, and there's no more resistors here and it goes back. It goes crawling back to the terminal. Now that's relatively fast, by the way. It's not crawling. Electricity is pretty fast. So the 0 volt right here, because it's been used up. So you started with 9 volts at the positive terminal, and what comes back is 0 volts. And that is why there is that push. That's the maximum pressure that's happening right here. That's why we call it the EMF, the electromotive force, which is, we talked about previously, not a force, but a pressure. So a couple of new terminology here. V drop and V rise. So V drop is the voltage that is entering the resistor, and the V rise is the voltage that is exiting the resistor. Okay, so that is those are the 3 rules for resistance in series. I'm going to give you a pretty neat summary later on. Now we're going to move on to parallel circuit. So again, just to review the series circuit, there is only one conducting path for the current to follow in that circuit. In a parallel circuit, there are 2 or more conducting paths for the current to follow. So in a parallel circuit, the resistors are wired in such a way that the same potential drop is applied to each resistor. Now, I'm going to need to explain this with a diagram. I'm going to make a diagram here, and it's always a good idea to start with your power source. So here's your negative and your positive, and I'm going to start with my power source. Let's come up with the same example that we did previously, except this time it is in parallel. So I'm going to put my R1 here, and I'm going to have to make 2 or more conducting paths to follow. So let me just draw this first, and I will explain why this is a parallel circuit. I put R2 here, R3, and R4. Make sure that when you're drawing a circuit schematics, you don't skimp on space. This is where you actually need to have a large enough diagram so that you don't mess up your conducting path when you're trying to do your Kirchhoff's rule analysis. Okay, so let's follow the circuit. Like follow the yellow brick road. This is the yellow brick road. So here we go. You have the current coming out of the positive terminal. It's happily going, and look at this. The current encounters a junction. It's like a fork in the road. So the current's going, should I go this way or should I go straight? That is right here. You got 1, 2, you have 2 paths to follow. That is the reveal right here. This is how we know that we have a parallel circuit. So the big question that any physics student always asks is, how do I know that this is a series circuit? How do I know this is a parallel circuit? Trace the current. That is the simplest answer. Just trace the flow of current, I. Because the reason the circuit is working is because the current is flowing. If you stop that flow of current, there is no circuit. Recall that a circuit has to have 3 parts. You have to have a source, which is the battery or the outlet, AC or DC, and then you have to have a path, which is the wire, the conductor, and you got to have a load. So current needs to be going through all those 3 things so that you can have a circuit. If one is missing, there is no circuit. Same thing goes here. Current is going. How should I go this way or should I go that way again? More than one path to follow. And that is how you know this is a parallel circuit. I'm going to use the same value for the R1, which is 10 ohms. This is 20 ohms, 30 ohms, and this is 40 ohms. And we're going to use 9 volts right here. So current is trying to turn on this resistor R1. Again, in order for this to turn on or to power on, you need to go back to the negative terminal to complete that cycle. So here it is. This is one path. Current comes out of the positive, okay, goes through R1, but again, it's not on yet because the current actually has to go through one full cycle. Once it goes back here, okay, so there's the 9 volts. 9 volts powers up the R1. So by the time it goes back here, how many volts does it have to have? 0. So you start with the maximum volts, you go back to the negative terminal with 0 potential difference. And that creates the maximum pump, maximum pressure. So that's done. But the second path, it can go through this R2, okay, go through and bypass R1 completely, then go back to the terminal that way without having to have anything to do with the R1. So the 9 volts is not going to get any weaker because it's only fighting one resistor at a time, unlike in a series circuit, because they got to go through the same conducting path. There's no choice. You got to take the same road every single time. This time you have a choice. You have different ways to get back home. Okay? Remember, the current comes out of the positive terminal. All it wants to do is go back home to the power source through the negative terminal. It doesn't have to go through every single path. It has many different paths to follow. It will take the easiest way home. Okay, so the same thing here. So this R1, so the V1 is going to be 9 volts. V2 is also going to be 9 volts because it has nothing to do with R1. You can cover it completely. See now I'm going to cover this and you have R2 all taken care of, one full cycle. The same thing with R3. 9 volts going to go here and completely bypass R2 and R1. So V3 is also 9 volts, and the same thing for R4. So they're all taking their solo path back home. There's no weakening. They only got to fight one resistor at a time. And it doesn't have to do with how strong the resistor. Whatever potential difference you get is what you're going to get when you take those single path. Okay, so what is the same as the total in a parallel circuit? So for resistors connected in parallel, this is the main thing, is that the individual V is equal to the total voltage. There is no weakening of the potential difference. That is the most important thing. I go back 2 minutes ago, we were talking about the series circuit and what is the same as the total of the components. It's the same. It's the same current. In a parallel resistance, in a parallel circuit, what is the same as the total is the individual voltages. So they will have the same one. So VT equals V1 equals V2 equals V3 equals V4, because they have multiple paths and they don't have to go through each individual one. The current, however, look at the current here. Some of the current will go this way. Some of the current will go that way. If they are all turned on, let's say there's no switch or all the switches are turned on, the current will split. So the current splits in a parallel circuit. So that means the total current is going to be the sum of the individual currents. It's going to be shared. Okay. When it comes to resistance, the RT together to fight the flow of current. So you're going to take the reciprocal to calculate the resistance. So 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So again, take advantage of your calculator buttons, the x to the negative 1 or 1 over x. Use those buttons. So let's calculate the total resistance of this circuit. So I'm going to do the 10, negative 1, plus 20 to the negative 1, plus 30 to the negative 1, plus 40 to the negative 1. And I got 0.208, and I have to inverse that one more time. So my equivalent or total resistance is 4.8 ohms. Now this is a neat thing because the lowest resistor has 10 ohms. But when you combine it with all these other resistors, you actually get a lower resistor than the lowest resistance that you have. So what does that tell you? In a parallel circuit, the more resistors you have, the lower the resistance you're actually going to get. So they're not working together to fight the flow of current. They're actually helping the current flow by keeping the potential difference the same through each of them because they're taking different paths. Once we've calculated the total resistance and we know the individual voltages, we can then bring in our Ohm's law and calculate the individual currents. So the current is going to be different than the total current, unlike in a series circuit. So let's calculate I1. So this will be V1 over R1, Ohm's law. So V1 is, they're all going to be 9 volts. The resistance is going to be different. So this is 10. So 9 divided by 10 is 0.9 amps. Okay. I2 is 9 volts divided by 20, which is 0.45 amps. I3 is 9 volts divided by 30 is 0.3 amps. And lastly, but not the least, I4 is 9 divided by 40, which is 0.225 amps. Let's take a look at the value of the current compared with the value of the resistors. So I1 was the one with the least resistance of 10 ohms, and it's got 0.9 amps. The one with the highest resistance of 40 ohms is the one with the least amount of current. Think about why that makes sense. Remember that the resistance or the resistor is actually resisting the flow of current. So if R4 is the strongest one of all these resistors that we have here in this circuit, R4 is going to fight back the hardest. So current is not going to be flowing the most through R4 because it is actually fighting the hardest. Now, if you were to add I1 and I2 and I3 and I4, you should get the total current. Now, did we calculate the total current? We have not. Okay, so what is our IT? VT over RT. So VT is 9 volts divided by total current is 4.8. we have 1.875 amps. That is the total current that we are getting in this circuit, 1.875, just so we can see zero point 0.9 plus 0.45 plus zero point 0.3 plus 0.225, and that gives you 1.875 amperes of total current. Again, this proves that the individual current add up to the total current of the circuit because the current splits while the voltage is maintained in a parallel circuit. So what's good about using a parallel circuit? Let's review. Parallel circuit, why is it good? Because you can choose to have some of your electronics on and some are off, so that if you're watching TV, for example, it's Netflix night, you want to turn on your TV, but you want to turn off your lights. You can do that in a parallel circuit. In a series circuit, if you turn off your light, that will turn off the TV as well and everything else in that circuit. So parallel resistance is great that way because some can be on and some can be off. That is the easiest analysis of a parallel circuit. But the good thing about a parallel circuit is that the voltage is maintained. The VT is maintained because every single one of the load will be getting the maximum potential difference that you're getting from that power source. However, if you have let's say you have your refrigerator and you plug it in into your outlet at home, your outlet at home is gonna give you 120 volts of potential difference. Of course, that big box outside on the street, or it could be underground if you live in the city, or it could be overhead in one of those tall towers or posts, that's going to be probably 10,000 volts of potential difference. But when it enters your house, it is going to be taken down using a transformer from 10,000 volts to 120 volts of potential difference. Now you plug in your fridge, for example, that fridge is going to require more than 120 volts of potential difference. So there is a device inside your fridge that will kick it up to whatever potential difference that that device, that appliance needs. So it's called a transformer. I will write that down later. All the devices that we need so that we can have the power that we need. So the voltage though is maintained because the VT is equal to the individual voltages. No weakening in a parallel circuit. The current is split, which is good because it's what we pay for. So current is actually, you're gonna save current if you're using a parallel circuit because the current is going to split as you encounter a junction along the conducting path in the circuit. So here are the 3 cardinal rules for resistance in a parallel circuit. So current is split, voltage is maintained, and the resistance is the reciprocal. So current splits in a parallel circuit, the voltage is maintained, and the total resistance, you take the reciprocal, so the RT is actually less than the lowest resistor that you have, which is pretty amazing because it's going to actually lower the resistance of the circuit as you put more resistors in that circuit. Okay, so let's do more examples. This is actually pretty fun to be analyzing a circuit. It's called a circuit. It's a circuit game. Circuit analysis. Okay, so here is an example of a parallel circuit. So let's see how many resistors do we have. You have a 6 ohm and a 4 ohm resistor connected in parallel with a 12-volt battery. So I'm going to call this R1 and R2. It doesn't matter as long as you stick to your convention. Makes sense to me that you call the first one 1 and the second one 2. We are going to, of course, assume that the battery itself doesn't offer any resistance to the circuit. Of course, the more stuff you have there, the more you're going to have resistance. We look at the resistors that as the device that actually resists the flow of current, but I'm going to mention now at this point that every single thing that you put there, that would include the wire, the copper or whatever conductor that you're using, all those things are going to offer some sort of an internal resistance. And that is one of the reasons why you don't want to be using an extension cord with some of the high voltage, high ampere electronic device or appliances. An example would be your dryer, your stove, your oven, your washing machine, your refrigerator. They should actually have their own circuit at home, not connected to any other circuits in that building. And they should never be plugged into an extension cord, even a power bar. It should be directly plugged in into the wall, because we're trying to eliminate any more resistance than they already have. Of course, the device that actually needs to heat up, an example would be those Thomas Edison, the Edison light bulb. They actually warm up the room. They use them for incubating, for example. You actually need not just the light, but also the heat. Appliances like stove, oven, and dryer and refrigerator, because it actually has to remove the heat from the box itself to cool down your food. They actually need to have some heat in them, and those are high resistance and high voltage. Therefore, the higher the resistance, you need to have higher voltage to operate them. So no extension cords for those ones because of internal resistance. All right, so we have 5 questions in this one. We need to find the equivalent resistance, which is the RT. We need to find the potential difference across each one. So we're going to look at the individual V. Find the current delivered to each. So we're going to look at the individual I. Find the power dissipated, looking at the individual power, and find the total power delivered to the resistor by the battery. In order for us to do our circuit game, our circuit analysis, we need to have a schematic first. So we're going to have to draw this circuit first and trace the flow of current so that we can analyze the circuit in terms of all these things that we need to find: resistance, voltage, and current, and power. Okay, so we have 2 resistance in this case. There are many ways to draw a circuit. Oh, this is a series circuit that I was starting with. So I'm going to draw this as simple as I can. And I'm actually going to draw this many different ways. I'm going to just or that one, simplify this. So I'm going to start over again. Start with your battery. This is a parallel circuit. We only have 2 resistors. So here's one. And of course, you can draw this many, many different ways. There's endless possibility. It just depends on what kind of circuit do you want to have, depending on the room that you're going to put the circuit in, where you want the switches and where you want the wires located. As long as you can trace the current, and again, this is the positive, this is the negative, and as soon as you get into this junction right here, you know right away that you got more than one conducting path to follow. There you go. You have a parallel circuit. There's your EMF. This is our R1, 6 ohms. I'm not gonna worry about the significant figures at this point. I'm just gonna put the 6 ohms there and the 4 ohms. Okay, and we have 12 volts of potential coming out of that battery. So we need to find the equivalent resistance. So question A, the total resistance of this is 1 over RT is 1 over 6 plus 1 over 4. Now we need to find the reciprocal of this. So 6 plus 4 equals, and then find the inverse of that again. Inverse is 2.4 ohms. Again, lower than the lowest resistance. So that's A done. For question B, find the potential difference across each resistor. Forget about Ohm's law. With this one, we just need to know that Kirchhoff says that because this is a parallel circuit, and I know the VT is 12 volts, then I know V1 is equal to V2 is equal to VT. They are going to each receive 12 volts of potential difference from the EMF. So that's done. Question C, find the current delivered to each resistor. So we have, we're looking for the current now. The current is going to split, so we need to find the individual ones. This is now bringing in Ohm's law. V1 over R1. So V is 12 volts divided by R1 is 6 ohms. So this is going to get 2 amps. Now, what do you predict is going to be the I2? Will it be higher or lower than 2 amps? Oh, this is V2 over R2. V2 same, 12 volts. Divided by, this is 4 ohms. This is going to receive 3 amps. Why is I2 greater than I1? Because it is a weaker resistance. It's going to allow more current to go through. So C is done. Question D, find the power dissipated by each resistor. So now we go back to our formula for power, electrical power, P equals IV. So I, we now know, is 2 amps and the volts is 12 volts. So this is going to be 12 times 2 is 24. And what is the power unit? What is the unit for power? I just told you it's watts. 24 watts is the power for the first one. That's P1. So P2 is I2 V2. So I2 is 3 amps times 12. This is going to be 36 watts of power for P2. D is done. E, find the total power delivered to the resistor. Question E, you have 2 ways to solve for this one. One is to directly plug in your IT times VT. The total current is, what is our total current? Total current, did we calculate our total current? Well, we have our individual ones. So 2 plus 3 is 5 amps. I'm actually going to show you if I were to calculate our total current. IT right here is VT over RT. VT is 12 volts and RT is 2.4 ohms. So 12 divided by 2.4 is 5 amps. Or we could just calculate them individually and add them up. So 5 amps is our total current and the total volts is 12 volts. So 12 times 5 is 60 watts. That's one way. Or we could just add the individual power that we already have calculated. So we have 24 plus 36. Check. You get 60 watts of power. Done. Isn't that fun? This is pretty awesome. It's like analyzing a game. It's like one of those maze circuit analysis. So I'm going to summarize the cardinal rules for series and parallel in a chart. So this is something that I made up years ago. You will not find this in a textbook. So I call this the Vazizarad. So start with, so there's your VIR. So these are obviously, you can see the subscript. These are the total. So the total voltage, total current, and the total resistance. And the Vazizarad that I'm speaking of is this. Vas Isa Rad, something fun that I thought of way back. Vasisa Rad. And you start with a series. So series is a simple one. Parallel can get complicated. So you just put a series and parallel and you just go Vasisa Rad. What does that mean? It's a little mnemonic, just a little something to help the brain. Okay, so the total voltage, what does that mean? A means you add the individual voltages. So what does that mean? Your VT is equal to V1 plus V2 plus V3 and so on. V a million. How many do you have? It doesn't matter. You're just going to add them all up and that will give you the total voltage in a series. That's what the A stands for. S means the same, not subtract, same. So what does that mean? It will be the same. So VT is equal to V1 equals V2 equals V3 equals whatever that is. That is what happens in a parallel circuit. The voltage is the same. And this is again something that I like to ask is, what's the same? Well, in a parallel circuit, voltage is the same. In a series circuit, what's the same is the current. So current is the same. So that means IT equals I1 equals I2 equals I3, and it doesn't even have to matter what resistor they have. You could be dealing with 5 ohms, you could be dealing with 5 mega ohms or 5 giga ohms. It doesn't matter. The current is going to be the same. And this is, you add the current. So IT equals I1 plus I2 plus I3 and so on. That's the case in a parallel circuit. What about the total resistance, RT? In a series circuit, you just add them all up. That's pretty simple. R1 plus R2 plus R3 and so on and so forth. That is the total resistance in a series circuit. This one, there's some division involved, so or inverse. So D1 divided by RT equals 1 divided by R1, 1 divided by R2, and so on and so forth. There you go. Vasisarad. Kirchhoff's rules in a chart. Pactcan style. And that brings us to the end of lesson 3, Kirchhoff's rules in a nutshell. This lesson goes hand in hand with the lesson that I gave yesterday. So I thought I'd tackle Kirchhoff's rules first before we look at a series and a parallel circuit. So make sure that you watch lesson yesterday first before you tackle more complicated series and parallel circuits. So the only way you can actually really master this is to do the exercise questions on page 24. So if I would like you to try all these questions on pages 24, 25, and take a picture and email them to me at mpactcan@wsd1.org, and I will take a look at your work. And that is the end of this lesson.
Dylan's dropping off his drunk friend in our area, so